everyone. I think we're waiting for a few people to join, but we'll go ahead and get started so we keep us all on a good pace. Good evening, and thank you for coming. Welcome to What's Up with the Arctic, our first Destinations and Discovery Series talk, which is sponsored by Cavalier Travels and the University of Virginia's Office of Engagement. My name is Kevin Conley. I'm the director of UVA's Alumni and Parent Travel Program, Cavalier Travels, and I'm pleased to introduce this evening's speaker, Howie Epstein, Professor of Environmental Sciences and Chair of the Department of Environmental Sciences. Howie's current research efforts are in the Arctic tundra of North America and Russia and the temperate forests of the US mid-Atlantic. In the Arctic, he examines the recent dynamics of Arctic tundra vegetation in response to changing climate and disturbances and the effects that these vegetation changes have on other Arctic ecosystem properties. In past talks with Howie, I've learned that he goes into very remote parts of the Arctic tundra, and so I think you'll find it very interesting, as I will. Howie accompanied Cavalier Travels trips to Alaska in 2015 and to Iceland in 2018, and he will likely be traveling with us to Antarctica in 2023. We're still working on the details of that one. During the webinar, please use the Q&A feature, which is you should find at the bottom of your screen, to post questions that Howie will try to answer toward the end of the program. We'll post resources in the webinar chat. This program is being recorded. This program is being recorded and will be posted on the Cavalier Travels webpage. And now I'll hand over the program to Howie Epstein. Howie?
Hi, everybody. I'm Howie Epstein from the Department of Environmental Sciences, and today I'm going to talk to you about what's up with the Arctic. Before we do that, first things first, we are going to define what is the Arctic, and the Arctic can be defined in a variety of different ways. If you look at the map on the right, you're seeing a view from above the North Pole. This might be a little bit different from views of the Earth that you're used to seeing. But one of the things that you can see first is that the Arctic is dominated by the Arctic Ocean. The Arctic Ocean is predominantly ice covered. We know that's changing, and we're going to talk about that later. Surrounding the Arctic Ocean are the Arctic land masses, and those land masses include a few different biomes of the Earth. We have the Arctic tundra, which is the northernmost land masses. To the south of the Arctic tundra, we have boreal forest vegetation, which is also known as taiga. The Arctic is underlain by permafrost, which is permanently frozen ground, and we're going to talk more about permafrost later. And that permafrost can be continuous permafrost, discontinuous permafrost, or sporadic permafrost. The Arctic has a lot of areas that are still pristine wilderness. It's home to some very charismatic fauna, megafauna. It has some of the world's most productive fisheries, and also, as we know, some of the most productive oil and gas extraction facilities that we have on Earth. The Arctic is home to 8 nations. So 8 nations sit above the Arctic Circle. The United States is one of those nations. And those nations form an international body called the Arctic Council. And interestingly, the seven nations of the Arctic, not including Russia, have recently decided to suspend Arctic Council activities in light of what is happening in Russia and Ukraine. The Arctic is home to a variety of different indigenous peoples and also non-indigenous peoples. And 5 major world rivers run through the Arctic and empty out into the Arctic Ocean. One of those is the Yukon that runs through Alaska. So there are different ways, as I said, different ways to define the Arctic. One is by the Arctic Circle. So the Arctic Circle sits at 66 and 2/3 degrees north latitude. And the Arctic Circle is defined in such a way that if you are above the Arctic Circle, you have at least one day where the sun never sets and at least one day where the sun never rises. Another way of defining the Arctic, a common way, is by a temperature line or temperature isotherm. If you look at the map again on the right, that red line is the July 10 degrees Celsius average temperature isotherm. So that everything that is north of that line could be defined as the Arctic. Also, a definition could be the latitudinal tree line. So everything that is north of where trees exist latitudinally can be the Arctic. And probably the broadest definition of the Arctic would be the Arctic Ocean watershed. So those are all the inland water bodies and rivers that flow into the Arctic Ocean. So the Arctic is the home of the midnight sun, actually more specifically, the midnight northern sun. If you've spent your, if you've spent your entire life in Charlottesville, you've never seen the sun in the northern sky. The sun sets in the west, rises again in the east. If you do want to see the sun in the northern sky, then you have to go above the Arctic Circle. And so depending on how far north of the Arctic Circle you are, there'll be a certain number of days with continuous sunlight and a certain number of days with continuous darkness. And actually, we have a poll now that we're going to run for you. Can we do that? Here we go. First question, have you ever been north of the Arctic Circle? Do we have the results yet? All right. Wow, almost a quarter of you have been north of the Arctic Circle. That is impressive. All right, let's close that and we can move on. Okay. Oops, I cannot go any further. Oh, there we go. Okay, so moving on. Now we're going to talk about a variety of different elements of the Arctic. The first one we're going to talk about is sea ice. So you have a great image off to your right there. That's a satellite image from NASA showing the Arctic sea ice extent, as well as the Greenland ice sheet and some of the ice sheets and the glaciers in the northern Canadian archipelago. So the Arctic Ocean is largely covered with sea ice, although we know this is changing. We're going to talk about that later. The extent of the Arctic sea ice peaks in mid-March. So that is the maximum extent of Arctic sea ice. It's usually around March 15th. The lowest amount of Arctic sea ice is in mid-September. So that is around September 15th. And after September 15th, the ice begins to accumulate again. And so we're just past the peak extent of the Arctic sea ice for the winter. Sorry, I'm having trouble advancing, but there we go. Another element of the Arctic that's really important is permafrost. So the entire Arctic tundra is underlain by permanently frozen ground. So permafrost is exactly that. It's permanently frozen ground. It's not necessarily ice. So permafrost can contain ice, but it also contains other things. It can contain rock, it can contain soil, it can contain dead organic matter. So it's anything that is 0 degrees Celsius or below and stays that way for at least 1 year. So you have to go into your second year of being below 0 degrees Celsius to be considered as permafrost. But it is important to remember that permafrost is not just ice. It's everything that's below 0 degrees Celsius. So here's a soil pit that we dug down into the Arctic tundra. And you can see that we dug down about 60 centimeters. Until we hit the permafrost, and so that tape there is lying right on top of the top of the permafrost table. So it's not that deep to get to the permafrost. So another important element of the Arctic is tundra vegetation, and that's what I study. I'm a vegetation ecologist, and I've been studying tundra vegetation now for about 25 years or so. And maybe you're surprised that the tundra can be actually quite vegetated, and you can see here on in the photo that there are shrubs there. So the tundra is defined by the absence of trees. So if you have trees, you're not tundra, and so if there are no trees because of cold temperatures, then you're defined as tundra. But it does have woody plants, okay, and so it actually has quite a number of shrubs, and those shrubs can get pretty tall. They can be deciduous or evergreen shrubs, and they can grow to 2 meters to 3 meters in height. And so in the southernmost areas of the tundra, it's quite vegetated, and it's 100% vegetation cover. But the tundra will range from that kind of vegetation in the south to more of a meadow-like vegetation in the center or mid latitudes of the tundra. And then finally to the areas that you might imagine the tundra look like, which are some more barren landscapes in the northernmost areas of the tundra that include a high component of mosses and lichens. We'll talk about them a little bit more. You can see that there's a high degree of variability. If you get up in elevation just a little bit, it's pretty windswept and gets pretty barren. And then you go down the slope a little bit towards that creek to the right in that photo, and you can see you get a little bit more vegetation down there. I'm going to talk a little bit about tundra shrubs. They're really interesting, and they actually go pretty far north in latitude. You can find woody plants, so you can find these shrubs at 75 degrees north latitude or above, which is pretty far north. And I'm showing you here the two northernmost shrubs. The one on the left is Dryas integrifolia or octopetala, which is mountain or Arctic avens. That's an evergreen shrub, and I know it's hard to see, but beneath those pretty green leaves is wood. Okay, so there are stems beneath those leaves, so it is a shrub. It's a woody plant. On the right is Salix arctica, which is a deciduous plant, so that's going to drop its leaves in the fall. And that's Arctic willow. You can see the wood a lot better in the Arctic willow. It gets the wood is pretty defined and a little bit thicker than what you have in the Dryas. And neither of these shrubs grow vertically. Okay, so they don't grow upwards. They grow horizontally. They basically hug the ground. The last element of tundra vegetation that I want to talk about is the non-vascular vegetation. And by non-vascular, I mean that they don't have root systems. And I don't know if you can see my cursor, but this rust colored area in here, that's a moss. All this white colored area, that's a lichen. Lichens are a symbiotic relationship between an algae or a bacteria and a fungus. And so this is sort of a plot level photo of how mosses and lichens, this non-vascular vegetation, mixes in with other things like shrubs and sedges. So out of my area of expertise, but the Arctic is home to some charismatic megafauna. On the upper left, you have your polar bear, which is the keystone predator of Arctic marine systems. The habitat for the polar bear is the sea ice, and the polar bear is listed as a threatened species now, and that's because the sea ice is threatened as well. In the upper right are bowhead whale. The bowhead whale are a really important subsistence food source for many indigenous populations, including the indigenous populations, many of them in northern Alaska. And the bottom photos, to the left is the muskox, to the right is the caribou, and these are the dominant grazers in Arctic tundra. They're pretty amazing creatures as well, and they survive through the winter. There's in certain parts of the Arctic, as you saw, there's not a lot of vegetation. But they survive through the winter by burrowing through the snow and eating the lichen that sits on the ground surface. So both muskox and caribou really are heavily dependent on lichen as a food source. Okay, there are 40 or more ethnic groups of people that we can find in the Arctic. And well, approximately 4 million people, although that again, that will depend on how you define the Arctic. That might be a very narrow definition of the Arctic. If you expand the geographic boundaries of the Arctic a little bit, you do add a lot of people. So depending on how you define the Arctic, it could be on the 4 million to over 100 million people. On the photo on the top left is of Utqiagvik, Alaska, which is formerly Barrow, Alaska. And that is a coastal community in northern Alaska. It's actually the northernmost city in the United States. And so it sits right on the sea ice. You can see in that photo, it's probably not dead of winter because the sun is out, but you can see the sea ice on the left that abuts right up against the coast of Utqiagvik. The town on the right is home to 4,000 to 5,000 people. So it's actually a pretty well-populated area. And that's a mix of indigenous and non-indigenous peoples. And there's a lot of science that's been done in Utqiagvik, Alaska. It has had a scientific presence since the mid to late 1940s. Maybe in contrast, on the bottom right are the Nenets, nomadic reindeer herders on the Yamal Peninsula, which is northwestern Siberia. These are nomadic reindeer herders who move north and south with their herds of reindeer. They move to the north in the summer for the calving grounds and then back south during the winter. And this photo is of the Nenets who are they're choosing their reindeer to pull their sleds to move across the tundra landscape. So not unlike Santa Claus. And also, as we mentioned, another important element of the Arctic is energy production, which is quite common in Arctic areas. On the upper left is the Prudhoe Bay oil field, which is actually the largest oil field in North America. That's been in operation since 1977. It's well past its peak of production of oil, but it is still producing oil. And actually, the only road in northern Alaska goes from Fairbanks, Alaska to the Prudhoe Bay oil field on the coast. The Prudhoe Bay oil field sits on the coast of northern Alaska. On the bottom right, you've got the Bowhead gas field, which is on the Yamal Peninsula, which is also where the Nenets reindeer herders are. That gas field has been in production since 2012. And I worked on the Yamal Peninsula in Siberia for 6 summers from 2007 to 2012. And so I was there at the time that the Bowhead gas field was being developed and moving into production. Interestingly, the Nenets reindeer migratory routes go right through the gas field. So the migratory herds of the reindeer and the Nenets families that manage them are split up into what are called brigades. And they each have they each have their own defined migratory pathway. And 2 of the brigades go right through the Bowhead gas field. And you can see here a photo of one of the Nenets reindeer herders moving some reindeer below the gas pipelines on the field. A really interesting element of the Arctic, and that many of these things are really ubiquitous and found all throughout the Arctic, are what we call pattern ground. And so these are cool features that are formed in the Arctic naturally due to the freezing and thawing of water. And the first one that I have up here are called ice wedge polygons. And if you can see my cursor again, the edges of these polygons, okay, those are wedges of ice that go into the ground and can go below the ground for several meters. And they're formed naturally. They're formed naturally because the permafrost cracks as it gets really cold. And when it cracks in the summer, it'll fill up with water. And when it freezes, that crack will expand, and then it will melt again in the summer and will fill up with water again. And then it will crack, and then it will expand, and then it will crack again. And so over time, you get these patterns of polygons. And these are called low-centered polygons because maybe obviously the center of those polygons are a depression and they're filled with water. For scale, these can be about 5 meters wide to tens of meters wide. So they're pretty large features, and there are billions of them all over the Arctic. And over time, these low-centered polygons, the center will fill up with vegetation and dead organic matter, and that will cause them to build up and rise, and they will turn into high-centered polygons. And this is what high-centered polygons look like. And those ponds will drain in the center, but you still see the wedges. You still see the edges of those polygons, which are still wedges of ice. Another really interesting feature that is also quite ubiquitous around the Arctic are called frost circles. And these are a little bit smaller. So these are maybe a meter in diameter, and they really look alien. And they look like it just looks like very bizarre features and how they can be formed naturally. But frost circles are formed by the freezing of water and the fact that the water doesn't freeze homogeneously across the landscape. So some areas are going to freeze more water faster than others. And when they freeze that water, the ground surface actually expands. It can expand by 20 centimeters or more. And when it expands like that, you might imagine the vegetation that sits on there will have a really hard time surviving. So you get these bare spots where vegetation can't make it, and then you get the areas that don't expand as much in between those where there is vegetation. So these are really interesting features, and I've spent many, many years studying frost circles and frost circle landscapes, and also ice wedge polygon landscapes. A less common feature is something called the Pingo. These are much larger features and much less common. They have a solid core of ice, and they're formed when a large area of water freezes and pushes the ground surface up, almost like an eruption. And so they look sort of like volcanoes, but they have this solid core of ice, and they can be 50 meters high. They can be 50 to 100 meters wide. So they're really large features. They are not very common, so you don't often see pingos on the landscape. Okay, so we've gone through many different elements of the Arctic system, and now we're going to get to the second part of the talk, which is, okay, what is up with the Arctic? And in this part of the talk, I'm going to use a few more graphs and some more data for you. So the first thing that we're going to look at is surface air temperatures. So these are surface air temperatures from 1900 to the present, and they're compared to the 1981 to the 2010 mean, which is a very common thing to do in climatology. And the red line is the Arctic. The green line is the global average temperatures. You can see both of those are increasing, but you might also be able to notice that the Arctic temperatures have increased about twice as much as the global average from 1900 to the present. So Arctic air temperatures have increased approximately 3 degrees Celsius, which is maybe about 6 degrees Fahrenheit since 1900. And that's compared to probably not quite, but close to 1.5 degrees Celsius for the globe. The process by which the Arctic is warming to a greater extent than the globe is called Arctic amplification, and we're going to talk about that in a few slides. And there's a great deal. While there is summer warming in the Arctic, a lot of the warming is not during the summer. Probably most of the warming is in the winter, and we see warming in all 4 seasons. So we see warming in fall and spring as well. A lot of the information that I'm going to show you over the next few slides comes from the NOAA Arctic Report Card. The National Oceanic and Atmospheric Administration, they put out an Arctic Report Card. They've been doing it every year for a number of years, and it is a great reference, and you can find it online. Okay, so the next thing that we're going to talk about is sea ice. So let's look at the maps on the upper left first. You can see the maximum extent of sea ice, and that's from March, this from last winter, so March 2021. So you can see that the sea ice covers nearly, it covers the entire Arctic Ocean at its maximum extent in March, and covers a little bit beyond the Arctic Ocean as well. If you look to the figure just to the right of that, that is the September 2021. So that's this past September sea ice extent, and that's the minimum sea ice extent. And so you can see where the melting of the sea ice occurs. There was a question that was posed prior to this about the sea lanes and transportation throughout the Arctic, and you can see that the fast ice, the ice that is hanging onto the land, is largely in the Canadian archipelago and northern Greenland. And there's a lot of open water in northern Alaska and the Scandinavian and the Russian Arctic. And this is pretty much the pattern that you see with the intra-annual variability of sea ice extent. So those areas that are open water are typically the open water from year to year. The Northwest Passage has opened up, and it has been navigable, but it's a much harder route than the other routes. Now, if we look at the graph to the right, the red line is the September, so that's the minimum sea ice extent, and the black line is the March, so that's the maximum sea ice extent. You can see they're both declining over time. The record it begins in the late 1970s. We're getting these data from satellite. And you can see, if you look at the March, if you look at the black line, the maximum sea ice extent has declined from the late 1970s through the present. But the greatest decline that we see is with the summer sea ice extent. And some actually a very dramatic decline. And it really raised the eyebrows of the Arctic community in 2007, when there was a really large drop in sea ice extent. Since 2007, it really hasn't recovered and has stayed at about those levels over that period. So the 15 lowest sea ice extents since 1979 have occurred in the last 15 years. So that's 2007 to 2021. The lowest recorded winter sea ice extent was the 2016-2017 winter, and the lowest summer ice sea ice extent you can see easily on that figure was 2012. All right, so let's talk about the Arctic amplification, which occurs in part from something called the ice albedo feedback, which I'm going to illustrate for you in this figure. So ice is one of the most reflective surfaces that we have on the planet. 85% of incoming solar radiation is reflected off the ice surface and goes back out into space, whereas only 15% of the incoming solar radiation is absorbed by the ice. If you compare that to open water, only 17% of the incoming solar radiation is reflected off of an open water surface and goes back to space. 93% of that solar radiation is absorbed by the water, which warms the water, and that warming water will radiate and continue to warm the atmosphere. So if you look at the flow diagram that I have on the right, it illustrates a positive feedback. Positive meaning that it feeds back on itself to continue. It doesn't mean a good feedback. So we have Arctic warming, which leads to the melting of the sea ice, which leads to the lower reflectivity of the ocean surface, which increases ocean absorption of solar radiation, which will ultimately lead to increased atmospheric warming, and then the cycle continues. This I thought was really interesting. It's some new data. I pulled the Arctic sea ice extent from this current winter, and it's been noticed that the date of the maximum extent of Arctic sea ice was rather early this year. The maximum sea ice extent occurred on February 25th, and you can see that on the blue line on the graph there that I've highlighted with the dashed vertical line. The earliest on record is February 24th, so it's pretty early, and the typical maximum for the winter sea ice extent is March 15th. So we're pretty early, but interestingly, the early melting does not necessarily correlate with the summer sea ice extent. So a lot can happen between now and September 15th. So we don't know what this necessarily will bode for summer sea ice. So we'll be looking out to see what happens with summer sea ice this year. Another variable that has been changing pretty rapidly and pretty dramatically is the snow cover in the northern high latitudes. These graphs show you May and June snow cover extents relative to the 1981, 2010 mean. May graph is on the left, June graph is on the right. The North American Arctic is in the black line, the Eurasian Arctic is in the red line, and you can see that the snow cover extents are decreasing pretty extensively. Those numbers are millions of square kilometers. It seems to be decreasing to a greater extent in the North American Arctic than the Eurasian Arctic. You'll see the Eurasian Arctic values have gone up a little bit, recovered a little bit in the most recent years. But people who study snow extent are continuing to monitor this. So May and June snow cover extents have decreased dramatically, particularly since about 2000. And then we also have a snow albedo effect, which adds to the Arctic amplification. So it's very similar to the sea ice. Snow is a very reflective surface. So if you remove the snow, you go from a very reflective surface to the ground, which is actually a very absorptive surface. So you warm the ground instead of being reflected off the snow. The warming ground will then radiate out and warm the atmosphere. Another change that's occurring in the Arctic that I wanted to point out to you is what's going on with the Greenland ice sheet. If you look at the graph on the bottom left, you see that the mass of the Greenland ice sheet is declining very rapidly. You can see the seasonal cycle in the mass of the Greenland ice sheet. So the mass will decrease in the summer as it melts, and then it will increase in the winter as some of it refreezes, and you get that intra-annual cycle from melt to refreeze, but the trend here is clearly one in the downward direction. So the Greenland ice sheet has lost 5,000 gigatons of mass over the past 20 years. This line goes from 2002 until the present. If you look at the map on the upper right, that shows an increase in number of melt days. So days, the days of the summer that where the Greenland ice sheet is experiencing melting. And you'll see that a lot of that is occurring on the fringes, on the edges of the Greenland ice sheet are experiencing a pretty dramatic increase in the number of days that they're experiencing melting. And all of this has big implications for sea level rise, in contrast to the sea ice extent. So if the Arctic sea ice melts, it doesn't really lead very much to sea level rise, because the Arctic sea ice is already displacing water based on its mass and volume. So if the Arctic sea ice melts, the water level will drop, and then the water that it creates will then increase the sea level, but it'll be about a wash. So the Arctic sea ice melting doesn't really contribute to sea level rise, but the Greenland ice sheet melting does, because you're taking water, you're taking ice from the land and turning it into water that then goes into the ocean. So that does contribute to sea level rise. All right, let's get back to talking a little bit more about permafrost. As I said, permafrost is permanently frozen ground. It is everything that is 0 degrees or less for more than a year. If you look at the map off to the left, you can the purple area, the darker purple area, is continuous permafrost. So the entirety of the Arctic tundra is underlain by continuous permafrost. Permafrost underlies more than 20% of the northern hemisphere, and that also includes the Tibetan Plateau. The permafrost can be hundreds of meters deep, and as you go further down into the depths of the Earth, it will get warmer, and ultimately the permafrost will disappear. But it can be hundreds of meters deep before that permafrost disappears. Now the active layer is the top. Well, it's technically not permafrost. It's the ground above the permafrost that thaws every summer and then refreezes in the winter. The active layer can be tens of centimeters to a few meters deep. In that photo that you see there, you probably can't see the numbers on there, but that we dug down. Actually, we dug down into a frost circle, and that found that in the below the frost circle, the active layer was about, I would say, 70 centimeters. So we dug down 70 centimeters until we hit the frozen ground. I know this is a lot of graphs, but we can just sort of look at them in general to make a point here that permafrost temperatures are warming and the active layer is getting deeper. The 4 graphs on the left are showing you permafrost temperatures. So these are deep temperatures that are being taken from boreholes in permafrost. And you can see that sort of regardless of where those temperatures, ground temperatures, are being taken, the tendency is an increasing temperature. You know, and this may not be a big deal if permafrost temperatures increase from -8 degrees Celsius to -7 degrees Celsius, but it is a big deal if it goes from -1 degree Celsius to 0 degrees Celsius, because then you have a phase change of water from ice to liquid water. Graphs in the upper right are active layer depth, and you can see sort of a consistent pattern as well, that the active layers are getting deeper. And if the active layers are getting deeper, that means that some of the permafrost is being permanently thawed and is no longer permafrost. And well, the combination of thawing permafrost and the decrease in sea ice can lead to an increase in coastal erosion and have an impact on Arctic communities. The photo to the upper left is the thaw slump. There was also another question earlier about ground slumping or thaw slumping. This is a pretty large thaw slump that has occurred because of permafrost thawing and what we call thermal karst, which is the slumping or the collapsing of ground because of a temperature effect. And if you look at the photo on the bottom right, that's from Shishmaref, Alaska. Shishmaref, Alaska is an island community, and they voted in 2016 to move the entire community from the island to the mainland to avoid the effects of climate change. As I said before, permafrost is not completely ice, but the amount of ice that is in permafrost is really important. The more ice in the areas of permafrost that have more ice, those are the areas that are more susceptible to thermokarst and thawing and slumping like this. If you take a rock and you go from -1 degree Celsius to +1 degree Celsius, it's still a rock. But obviously, if you do that to water, you've changed the density and the structure of the material. Another important factor about permafrost and Arctic soils in general is that they store massive amounts of carbon. They store massive amounts of dead organic matter, as you can see in the photos on the left. Those are Arctic soils, and you can see that's predominantly dead plant material. And on the bottom left, there is a photo of me holding about 30 to 40 centimeters of Arctic soil, and that's mostly, if not all, dead organic matter. The map on the right there, that is carbon. That's the amount of carbon that is in the top 3 meters of soil. And we have actually relatively decent estimates of carbon in the top 1 to 3 meters of soil in the northern high latitudes. And the further north you go, the more carbon is stored in those soils, because the dead organic matter just doesn't decompose in the cold and relatively soggy climate of the Arctic. So that dead organic matter just stays around. Currently, the permafrost and Arctic soils hold about twice as much carbon that's in our atmosphere. So in the very unlikely scenario that all of that permafrost thaws and all of that carbon is released to the atmosphere, that will triple the amount of carbon that is in our atmosphere. Again, that is an unlikely scenario, but some of that carbon will get thawed and will be decomposed and be released to our atmosphere. It'll either be released as carbon dioxide if the soils are not saturated and there's oxygen in the soils, it gets released as carbon dioxide. If the soils are saturated and there's not enough oxygen in the soils, then it would be released as methane, which is a more potent greenhouse gas than carbon dioxide. Okay, the last thing that I want to talk about in terms of changes in the Arctic is the vegetation. And again, this is my area of work. I study vegetation patterns and dynamics throughout the Arctic. And what we're seeing is that the Arctic is getting greener. So the vegetation is increasing in the Arctic. If you look at the graph at the bottom left, the y-axis is an index of greenness that we get from satellite data. So that's effectively how much vegetation there is. It's basically how green the landscape is. And if you look at the two lines in the center, if you look at the gray line and the black line, those are from two different sensors, and that's the average for the entire Arctic. And it goes up and down, but the trend is one of an increase. So the general trend is that the Arctic is getting greener. If you look at the other two lines, the top line is Eurasia, the bottom line is North America. Eurasia is on average greener than North America, but that's basically because the Eurasian Arctic sits further south than the North American Arctic on average. So the North American Arctic includes the Canadian archipelago, and that has much sparser vegetation than the Eurasian Arctic. But the trend is increasing greenness, and you can see in the map on the right, it'll show you the areas that are greening dramatically, the dark green areas. And then there are also some areas that are in brown where the vegetation has declined over time. Oh, one of the main culprits of this vegetation greening are shrubs. That's a Siberian alder, that photo there. And one of the things that we're seeing on the landscape that's causing this greening is the expansion of those tundra shrubs. One of the first studies, or maybe the first study to look at the expansion of shrubs in the Arctic was this Nature paper from 2001. They used repeat aerial photographs from the late 40s and 1950s and compared those with more recent photographs across northern Alaska, and found many of those repeat photographs were showing increases in shrubs. It's a little bit hard to see with the black and white compared to the green, but if you look carefully, you can see that there's a pretty decent amount of infill in the shrubs in the lower slopes and even on some of the slopes. So one of my graduate students wanted to see what was going on in Siberia. And so he utilized a really neat data source. He utilized spy satellite imagery that we had collected over the former Soviet Union in the 1960s and 70s. And these were the first spy satellite missions that we had flown in the 1960s. And those satellites would remain in orbit for a period of just a few weeks. They would take the images, which were actually quite high resolution, and they would eject the film canisters, and those film canisters would float down with these little parachutes, and we would fly and scoop them up in midair and bring them back. And Bill Clinton, under the Clinton administration, these classified spy satellite images were declassified, and many of them were made available to the general public in 1995 and others in 2001. And they're a great source for environmental scientists looking at Earth observations. And so here is an image from the late 1960s. This is in Siberia in the Taimyr Peninsula. And so you can see what it looks like. The very dark areas are water bodies. The next darkest areas that you see, those are shrubs. So those are Siberian alder. And the light areas are shorter statured tundra vegetation. And if we compare that from the 60s to a more recent image from the 2000s, this is a high resolution commercial satellite image. You can see, I'll toggle back and forth, but you can see there's quite a bit of change in the tundra vegetation and a pretty substantial expansion of shrubs. Here's just a photograph that I took on the Yamal Peninsula of Siberian alder, sort of marching its way across the landscape. And actually it's a frost circle dominated landscape. And it's kind of using those frost circles or the edges of those frost circles to make their way across the landscape. So that's sort of the end. That's sort of the end of my talk. It's a really hard talk to end because, I've just given you a variety of different ways that the Arctic is changing, many of them not necessarily in positive ways. So I thought before I get to my final slide, let's do another poll. So the question is, how concerned are you with the changes that are presently occurring in the Arctic? Results. Wow. All right. 80%, almost 80%, a lot. 2%, not at all. All right. Okay, I'll move to my last slide. After we run the poll, I think it takes my computer a minute or two to figure out what's going on. There we go. Okay. I'll end with this. The Arctic is a beautiful and complex place. It's changing rapidly, affecting all interconnected components of the Arctic system. We like to say that the Arctic is not like Vegas, which means that what happens in the Arctic does not stay in the Arctic. So the changes that we're seeing in the Arctic will have implications for the rest of the globe. And with that, I would be more than happy to take some questions.
Great, Howie. This is extremely interesting.
All right, I'm going to stop sharing and we can go back to gallery mode.
All right, you can hear me, correct?
I can hear you. You can hear me too?
I can.
All right.
We have some questions that have come in.
Okay.
This one is very interesting. I actually learned from this question as well. This is from Joanne. She didn't say what class year she is, but she is talking about basically magma shift issues. And so that the melting of the ice sheets was causing a sinking of other islands, such as Tangier Island in the Chesapeake Bay. Squeezing the magma down was causing other islands to be boosted above sea level. Okay, so it's a little bit out of my area of expertise, but I think that those islands are I think those islands are being affected by sea level rise, because
the weight of an ice sheet, like the weight of a Greenland ice sheet or the weight of an ice sheet on a Canadian island. My understanding is that's going to weigh down on the land masses. So when those land masses, so the land masses that are losing the ice will see a rebound effect. But the land masses that don't have ice, that are seeing their land disappear, that I'm guessing that is sea level rise. So that is my understanding of what's going on.
Okay. We had another question earlier about sorry, from Bob. He didn't say where he's from, but he said that you use a lot of your graphs tend to show absolute changes instead of percentages. And I kind of understand why.
Yeah, good question.
But I can't answer it. So you answer.
Yeah, so I don't yeah, some of those I'm gonna know, and some of those I'm not in terms of percent changes. So I believe that the sea ice, I think we've seen something on the order, I'm going to say something on the order of 10 to 20% decline in the sea ice extent over that period of record. I think we're probably seeing the same with regard to the snow cover extent. I don't know about the volume of ice in Greenland. That would be really interesting. What volume of ice we're losing? I don't think it's a very large fraction yet. The Greenland ice sheet is massive, and we're seeing huge amounts of ice being converted to water. But there's a lot of ice there, to be melted. In terms of the vegetation greenness, I think we're probably also seeing on the order of 20%. Increases in greenness. The shrub extent, the greatest shrub extent we saw in Siberia was 25%.
Wow.
And interestingly, we didn't see any. Interestingly, we only saw one. We looked at 11 different areas in Siberia, and we only saw one that decreased, and it was actually a very mixed signal. The decrease in shrub and tree cover was because there was some flooding. But all the other areas were showing increase in shrub extent, and the maximum was 25%.
Okay, excellent.
Oh, and I can give you the carbon. I can give you the carbon number as well. So I know that I said that if all of the carbon in permafrost regions were to decompose and go into the atmosphere, that would triple the amount of carbon that we see in the atmosphere. That is not going to happen. But the estimates that we're seeing from models right now is about 5 to 10% of the carbon, 5 to 10% of the carbon that's currently stored in permafrost and active layer soils will be converted to CO2 or methane.
Okay, excellent. I remember I actually jotted down a question while you were speaking, because I remember when we were in Alaska in 2015, and you and Fran from Harvard, I can't remember her last name.
Fran Ulmer.
Ulmer, yeah.
Yeah.
Yeah. So you were talking about how all of the nations that had a piece of their shore in the Arctic Circle were part of this council. Could you just briefly talk about that? Because I don't think a lot of people understand that.
Well, they have a governing body called the North Slope Borough. I'm not sure if that's what we were talking about, but the North Slope Borough is an Indigenous governing body of all of the different communities that sit on the North Slope, which is the area of Alaska that's north of the Brooks Mountain Range. So, yes, there is a great deal of sort of collective sovereignty of the native communities in the Arctic.
Okay. And then we had a question from Lois, who's in College of Arts and Sciences from 1986, and she says that are current students engaged in work on this type of this topic?
Yeah, they are, and so a lot of students are engaged in this topic. I have a lot of undergraduate students working in my lab on a variety of different projects that we have going on in the Arctic. Some are remote sensing, so some are working on these satellite images that we're collecting. Others are doing simulation modeling of Arctic tundra. Others are working on field samples that we collected from the Arctic, both plant and soil samples. On some occasions, though, we do get to bring UVA undergraduate students up to the Arctic. It's challenging because we work in some really remote places, and it's hard to bring extra people to some of those locations. But I have brought UVA undergraduate students to the Arctic We had a few students working with us at the Toolik Lake Field Station, which is a Northern Alaska field station that's in the tundra on the North Slope of Alaska. And so we had a few undergraduate students working there. This summer, I'm actually bringing at least one undergraduate student to a taiga or boreal forest field site that's just outside of Fairbanks. And I have a project that just started about a year ago in Utqiagvik, Alaska. We're just sort of getting our feet wet on that project. We're actually, because of COVID, we're doing our first field season this summer. I don't think we're going to bring undergraduates there this summer, but if things go smoothly, then in future years, we'll try to bring some UVA undergrads up to the Arctic, up to Utqiagvik.
Excellent.
Yeah.
We have a question here from Karen Bonding from the McIntyre School of Commerce, whom I know you do some work with them, who retired in 2015. She's going to challenge us on the, not challenge us, but could you talk a little bit about the opening of the sea lanes that are north of Greenland?
Yeah.
And how that shortens shipping times and that sort of thing. I know it's a little bit, it's out of your expertise, but if you want to touch on it.
Yep, I will talk about it. I will talk about it a little bit more, and we'll make some inferences based on what we know. And this is a becomes a geopolitical question, I guess. But if you look at those, if you think about the transportation routes and where the sea ice is opening up, the entire Russian coast is open, is open in the summer, and most of the Alaskan coast is open as well, and so the Bering Strait is open. The Northeast Passage that might go up to the east of Russia, and then north and then west along the Russian coastline, that's open up as well. The water bodies between Greenland and Scandinavia typically tend to open up. Again, but that's in the peak of melt. The ice that seems to be hanging on is the ice in that Canadian archipelago. So, so the Northwest Passage might not be is not the best route, but a lot of those other areas are opening up, and they're opening up, for transport, and they're being used for transport. And where and some nations are going to be more open to building and populating areas and using those routes for shipping.
Yeah, and that brings
some nations are more likely to do that than others. Sorry, what'd you say, Kevin?
It leads us right into the next question from William, who's a Darden 1977 graduate, who says that he's basically who is best positioned to win amongst the US, Canada, Russia, and China from this battle for the Arctic. Well, I would say that Russia and China are probably thinking about the Arctic a lot more than we have in recent times. I know that the US is now putting a lot more attention into the Arctic, and I think part of that has to do with what's going on in Russia. The Arctic it has historically been a pretty important place with regard to global conflicts, and the dew line, the distant early warning line that we had throughout Alaska and northern Canada, that's a testament to that. And so I think that you're going to see a lot more attention on the Arctic coming from the United States. But historically, Russia has been thinking a lot more about the Arctic than we have. China has been thinking a lot about the Arctic as well. And those transportation routes they tend to be the ones that are open. So things are playing out interestingly recently. So your guess is as good as mine about how the whole thing will play out. But the U.S. cannot afford to ignore the Arctic. Mm-hmm. All right. Well, we have a question here, actually, that we do have one about the Antarctic, but first we're going to jump into another one about the Arctic, which is this is from Peyton, who's a grad from 1975, grad student, I believe. What is happening to the Arctic wolves?
Oh, Peyton, I'm really sorry. I don't have a great answer for you. I have not spent a lot of time looking at the Arctic wolves or studying the Arctic wolves. In fact, the only time I've ever seen an Arctic wolf was from a helicopter. I know that some of my field collaborators and colleagues have encountered Arctic wolves in the past, out in the field. But I'm sorry, I haven't really followed the Arctic wolves.
Okay. Sorry, I just thought I'd toss that in, see if you had.
I do know that the caribou populations right now are in decline. So we don't, they tend to fluctuate. But there are some good reasons why caribou and reindeer populations are declining, and that has to do with insects. It has to do with ground freezing, so rain freezing on top of snow, and that will prevent caribou from feeding on the lichens in the winter. So the caribou populations are in decline, and caribou are the dominant food source. Caribou and reindeer are the dominant food source for the Arctic wolves, or a dominant food source. And I don't know if the declining caribou population at this point is enough to affect the wolf population.
Okay. I have one last question here, I think, and then we'll let anybody ask about Cavalier Travels and programs that we have coming up. And this is from Tom Wood. It says, are the effects of warming in the Antarctic comparable to the Arctic, or are they different? And if they're different.
Yeah, that's a really interesting question. And the way to frame the question first is even though those are the coldest parts, the coldest parts of our planet, maybe throw the Tibetan Plateau in there, they're completely different beasts. So the Arctic, as we just saw, is an ocean that's surrounded by land. The Antarctic is exactly the opposite. It's a land with a massive ice sheet on it that's surrounded by water. So even though they're both extremely cold, the cold climates are actually really, really different between the Arctic and the Antarctic. So we actually don't expect we don't expect them to be responding similarly, or even to be warming similarly. And I think in the first sort of decade or decades where we saw the Arctic warming pretty substantially, the Antarctic was not doing a lot with regard to warming. It was pretty stable with regard to warming. That has changed, and I think we're seeing the Antarctic warm more now recently than it has in the past. We're starting to see some more decreases in sea ice in the Antarctic, and we're starting to see the loss of ice from ice sheets and on the Antarctic. So we're starting to see more warming in the Antarctic, and some of the effects of the Antarctic that we hadn't seen early on, where the Arctic was experiencing those things.
Great. Well, Howie, I'd really like to thank you for sharing your expertise on the Arctic and its effect on our global climate and whatnot. Anybody who's been particularly interested in what Howie's talking about, he is in regular rotation as a faculty leader on our Cavalier Travels trips. Those of you who traveled with us before know that we have faculty on every trip. And Howie's a good one for the Arctic and Alaska in particular, and we're working on Antarctica. Howie, thank you again, and we'll be in touch soon. And thank you for taking your evening, during the semester to give us this talk.
Yeah, you're all very welcome.
Yeah,
pleasure.
And let's see, I think we were going to put up a slide of what we have coming up. There it is. So I'm Kevin, director of the Cavalier Travels program, as I mentioned. We have a number of trips available this year. The world is starting to travel again, which we're very excited about. Number of our trips are sold out, but there's still information available on our webpage. Sicily, I believe, is sold out. Spain, the first Spain trip is sold out. But we still have a lot of availability on our other trips. So anyway, thank you everybody for attending, and thanks to the audience. We've had a great audience, and they stuck through all of it. So it's pretty good for an academic type of program. So thank you everyone, and hope you have a great rest of the evening and a great rest of the week. And we'll have another one of these in a few months. Take care.